Hey guys, I wanted to make a quick video summarizing kind of chapter 4 of what we're covering in this course. So here I've got a situation where my procedure is going to be pulling cards from a standard deck of cards. And that can be one card, two cards, multiple cards. It depends on what the situation is. So I'm going to walk through, I think, 5 different scenarios and walk through how to calculate probabilities, and it'll summarize everything we've covered for this course. First thing I want to talk about before we jump into the 5 different examples is what type of probability will this be? Remember, there's theoretical or true probability or statistical or observational probability. In this case, we're going to talk about theoretical probability. And the reason this is theoretical is because we don't have any data or statistics to look at. We're just looking at the theory of pulling cards from the standard deck. To remind you guys how to calculate the theoretical probability, it's always going to be based on a ratio, and the numerator of that ratio is going to be the number of good or ideal outcomes. That's going to be on the numerator for any type of probability when you're talking theoretical. The denominator of that ratio is always going to be the number of total outcomes. And this is important because this is typically the hardest part of calculating probability, is this determining the number of total outcomes. Now, there is a word for the number of total outcomes, and the word that we use for that is the sample space. So the sample space is typically the collection of all simple events, or all the smallest kind of outcomes you can come up with from one event, or one procedure. Sorry about that. So in this case, my sample space is all of the cards on the screen. So that's the entire set of cards. In this case, there's 52 total cards, and that's a good thing. So my sample space is equal to 52, and that's going to make my calculations really, really easy. All right. So the 5 problems that I'm going to look at are going to be randomly selecting a face card, randomly selecting a face card or an ace, randomly selecting a face card or a red card, randomly selecting a card, putting it back, and then selecting another face card. And then the last one, randomly selecting a red card, not replacing it, and then pulling another red card. So what you'll see, hopefully, is that you've got several different probabilities here. And I'm just going to identify which ones we're going to look at. This first one is just going to be the probability of a single event. So the probability of A. In this case, my event A is going to be defined as just pulling a red card, a face card. And that's what this first one is. Very basic probability, something you've probably seen hundreds of times in your life. The second example here is randomly selecting a face card or an ace. And that's going to be a probability of A or B. In this case, my A event is actually the same thing, selecting a face card or an ace. But that's going to be an OR probability. The next one is going to be talking about selecting a face card or a red card. So it's another OR probability. Again, obviously the events A and B have changed in each of these examples, but it's still going to be an OR probability. Number 4 is going to be a face card and then another face card. And whenever you're talking about something and then something else, now this is going to be a different type of probability. This is going to be the probability of that first event and then, and I'm just going to write out the words and then. Now remember, our textbook in the course typically just does this as P of A, the probability of the probability of event A, and the probability of B. Those mean the same thing, but for this course, or for this example, I'm going to write out the words and then. Hopefully you can see that the final example is going to be an additional event and then another event. And for the last one, I'm just going to put P and B. And I'm going to remember that that means P and then B. So let's actually go ahead and solve this first problem. So randomly selecting a face card. Here I've got my sample space set up. And I will remind ourselves that we're talking about theoretical probability. And to calculate theoretical probability, we need the ratio of all the good outcomes over the total outcomes. So what we're going to think about is all the good outcomes. Well, we got to count how many face cards there are in our sample space. And if I look at my sample space, I see that there are 3 face cards that are clubs, 3 diamonds, 3 hearts, and 3 spades. When I do the quick calculations, 3 times 4, or 3 plus 3 plus 3 plus 3, I end up seeing that there are 12 good outcomes that I'm looking for. All 12 of those I would be happy with, and I've got to divide that by the total number of outcomes, 52. When you reduce this ratio, you're going to end up getting 0.2307. Also accept the answers 0.231. I'll also accept the answer of 23.1%. I'd also take 23.0%. I'm not going to be picky about rounding decimals in that point. All right, so that's the first one. Now let's actually look at solving the next one. So now that was probability of A. Let's look at probability of A or B. So here I've got probability of an ace, a face card, or an ace. So again, it's going to be the probability of A or the B. In this case, my A is going to be drawing a face card. So I'm going to go ahead and identify this, draw a face card. And then my B, my event B, is going to be drawing an ace. So drawing an ace. B is draw an ace. Because I've got an or probability, I might want to refer back to my notes and remember that the formula to calculate calculating a or probability is the probability of A plus the probability of B minus, and that's the key here, you've got to remember the subtraction part at the very end, probability of A and B. And remember, this A and B is different. This A and B is talking about A and B at the same time. So probability of A and the little and symbol of B is A and B at the same time. That's very, very important. Now, let's go ahead and actually calculate some of these out. Using the same idea as before, where we're going to have the number of good outcomes, and we're going to divide that by the number of total outcomes. That's that same ratio for all theoretical probability. So now we've just got to go over here and calculate the chances of these things happening. So first one we're looking at is drawing a face card. Well, we can use this probability from the previous problem, or we can identify that there are 12 good outcomes, so 12 good outcomes out of the 52 total. All right, that's excellent. The next one we got to think about is drawing an ace. And in this case, if we go back to our sample set, our sample space, we can see that there are 1, 2, 3, 4 aces. So we've got 4 good aces that I'd be happy with. So our ratio for the probability of drawing an ace is going to be 4 out of 52. And then I've got to take out this last probability. I've got to take out this probability of them two happening at the same time. And the question I have to ask myself is, can you do both of these events at the same time? Can you draw a face card and an ace at the same time? Well, luckily, you cannot. The reason I say luckily is because it's going to make the math easier. But if you look at the face cards, are any of these face cards aces? No, they're not. So you cannot do both of those things at the same time. So in this case, the probability of A and B occurring at the same time becomes 0 out of 52. Now, the last step to these problems is just actually calculating that out. You can type this into the calculator. If you did, make sure that you type this in with parentheses. In the calculator, you'd want to do open parentheses 12 divided by 52, close parentheses, plus open parentheses 4 divided by 52, close parentheses. If you do that, you should end up getting 0.30769. Again, for this course, what I'm looking for is 3 significant digits. I would accept multiple answers here. I'd accept 0.308. I'd accept 0.307, even though that's not 100% correct. And then I would accept the percentage answers as well. So 30.8% or 30.7%. Either of those is correct. If you're looking for one that's more correct, technically 308 and 30.8 are more correct because you take that third decimal. You take that third digit and round based on the fourth digit. But this is not an arithmetic course. I'm not going to worry about it that much. All right, so that is the second problem. Now let's go ahead and look at the third type of probability problem. And in this one, it's going to be very similar. Sorry about that. This one is going to be very similar. It's an OR probability as well. And now we've got a separate situation where we've got a face card or a red card. So hopefully you can see that this is the probability of another A or B. But in this case, our A and our B are defined differently. Our A is going to be, actually our A is defined the same, right? Yeah, A is still drawing a face card. And then our B in this case is going to be a red card. All right, so we're going to do the same ideas as before. We're going to use that formula to calculate all theoretical probability. And we're going to take that the probability of A or B is going to be the probability of A plus the probability, I did that last time too, the probability of B minus the probability of A and B. And remember that A and B is talking about A and B at the same time. So now we actually have to go through and calculate these probabilities. probability of a face card. If you think about our sample space, we're talking about the number of good outcomes. Well, I've got 12 good outcomes here. We've done this now 3 times, I believe. So there's my 12 good outcomes. So my calculation for the probability of A is going to be 12 out of 52. Hopefully this is becoming old news to you, and you've got that stuff down. The next one's going to be a little bit different. This time, we have not calculated this one yet, the probability of a red card. So let's talk about how you can calculate the probability of a red card. We've got to look at our sample space, and we've got to talk about how many good outcomes are there. Well, if we look at our sample space, there are lots of red cards. All of these are red cards. If I count those up, that's going to be 26 out of 52. So my calculation for the probability of the probability of grabbing a red card is going to be 26 over 52. Again, the way I calculated that out, I'm using the same theoretical probability calculation that I did before. It's always just going to be the number of good outcomes. So in this case, I have 26 good outcomes because there's 26 red cards right up there at the top. You can count those if you'd like. And the denominator of all these probabilities is going to be the total outcomes. That's why that I've got that 52 on the denominator of that ratio. Some of you may see that, well, pulling a red card is I got a 1 over 2 chance. I've got 50% chance. And you could substitute in 1 over 2 or 50% for this ratio right here. But to keep things easy and simple for this video, I'm going to keep it as the original unsimplified ratio. All right. Last step on this problem is you've got to determine the probability of A and B. Sorry, I didn't close those parentheses earlier. That's bad math. So let's actually figure this out. This is the A or B at the same time. A and B at the same time. So if we look at our sample space, this is talking about face and red cards. So we've got some options here that are being double counted. What's really going on is those 6 red cards, we counted them in the face and we counted them in the red. So we've got those 6 red cards counted in both of these ratios. We've got them counted in the face cards. There's 6 in this 12 over 52, and there's 6 in this 26 over 52. So we've got to get rid of one of those double counts. So what we're going to do is we're just going to subtract off the chances of that occurring at the same time. So the chances of those happening at the same time is going to be minus 6 over 52. Typing that into the calculator should give you 12 plus 26 minus 6. I'm doing just the numerators because that's how you do fraction operations. And I get 32. 32 divided by 52. I'm doing that just on my calculator as you guys are watching. But I ended up getting, I'll write down what I ended up doing. It ends up getting 32 over 52. When you type that in as a ratio or as a fraction, you get 0.615. Again, I would take that answer. I'd also take the 61.5%. The key part of this problem is that you've got to identify this double count, this probability of A and B occurring at the same time. You'll see that when I calculated the probability of A, the chances of getting the face card, I counted all of these cards, including these 6 red face cards. And then when I did the calculation of the probability of a red card, I counted these 6 cards a second time. So because I've counted those 6 cards twice, I've got to subtract one version of those 6 cards. And that's what I ended up doing right here. And that's the best and the most important part of this OR probability. If you're following along with all of the examples, you'll see that on the previous example, we did not have any of those double counts. We had 0 for that double count part because these 2 options were impossible. The mathematical term for those happening are that they're disjoint events. They cannot happen at the same time. You cannot grab a face card and an ace at the same time. They're disjoint. However, in our example number 3, these are non-disjoint events because they can occur at the same time. All right, let's go ahead and move on to our 4th and 5th example. Next one's going to be talking about randomly selecting a face card, putting it back, and then selecting another face card. So in this case, hopefully you can identify that we've got 2 events here. We've got a probability of an A and then a B. So this becomes probability of A, and I'm not going to write out and then. I'm just going to put B and imply that that means and then. Go ahead and identify my 2 events. In this case, my probability of A is going to be a face card. And I'm going to go ahead and write out what happens in between these 2 events because after the face card, I put it back. This is very, very important that I'm putting it back. I'm going to go ahead and write that down on my little planning over here. to make sure that I remember that. So I'm going to replace. I'm just going to put replace because that's what putting it back means. And then I'm going to pull out my next event, and my next event, I got to remind myself, what is it? Selecting another face card. So that's another face card. All right, excellent. So to calculate the probability of any event of A and then B, the formula is going to be, there's two formulas you can use. The one that will always work is the probability of A multiplied by the probability of B conditioned on that A already occurred. All right, conditioned on that A already occurred. Now, you can always use that formula, just like you can always, on the previous problems, you can always use this formula. The one here, let me highlight it here in yellow. You can always use this formula. When it happens that the events are disjoint, the last part of the formula will turn into 0. On the second problem, those were not disjoint, or I guess the third problem, those were not disjoint, so we had a value for that final subtraction. But you can always use this formula for addition probability or probability. The same logic, you can always use this formula for and then probability. But there is an easier way to do this. This formula turns out to something much easier if these events are independent. And by independent, I mean that they do not affect each other. In this case, because pulling a face card, replacing that, and then pulling another face card are independent events, this formula does reduce to something much easier. You can just calculate the probability of A multiplied by the probability of B. That makes things much easier for us. Because we've already calculated how to find the probability of pulling a face card, we know that there are 12 face cards. So that just becomes 12. The 12 face cards and 52 cards total. So that just becomes 12 over 52. And then we know that because these are independent events, we can just multiply them directly across, or multiply them, the probabilities right next to each other. So it's just going to be 12 divided by 52 again. When you calculate that out, you end up getting 0.0532. I would take that answer. I'd also take 0.053, or the percentage answer would be 5.3%. Any of those would work. If you're thinking about this answer here and you're saying, oh, that's only 2 digits, it's actually 3. It's just because we've got that leading 0 there because we're at 5%. And that's why you only need one decimal place there. Okay, now let's talk for just a second before we move on to the next problem, I guess the last problem, of why you can still use this formula. And it's actually really cool because if you think about it, the first part of this formula is really straightforward. We've done it several times. The probability of pulling a face card. That's going to become 12 over 52. Then, using this fancy formula, the conditional probability here, I've got to determine the probability of B occurring given that A has occurred. That's what that means. So the probability of B occurring, remind ourselves what B is. B is just pulling another face card. So what's the probability of pulling another face card given that you pulled and replaced a card? Well, if you pull a card and you replace it, it shouldn't change what you pull on the next card. That's by definition independent events. So in this case, the probability of pulling a second face card, given that you pulled and replaced a face card, is still just 12 over 52. So we've actually done the exact same calculation using the exact same formula. And the reason we can do that is because these events are independent. And that's really important here, that these events are independent. Now, when you're solving problems like this, am I going to ask for you to identify immediately what's independent and what's not? Absolutely not. You'll be able to just do the calculations, and if you can do the calculations like we did here, then you don't have to identify independent or not. However, it may make things easier if you think about this as independent or not, and then you can just jump to, I circled the wrong one, you could jump to the independent calculation for P and B. But again, you don't have to identify independent or not. I think that you should be able to do the calculations as they are. Last problem I want to work through. Let's go ahead and talk through number 5. Oh, sorry about that. Let's see. Number 5. And now we've got another sample space. And let's see if we can... Yeah, there we go. Let's see if we can do this last problem relatively quickly. So randomly selecting a card, not replacing it, and then pulling another red card. Hopefully that you can see that this is, again, a probability of A and then a B event. In this case, my event A is going to be a red card. And then what happens after that red card is going to be a don't replace it. So no replace. And then my next event would be another red card. B is going to be another red card. So using the formula that we determined in class, the probability of A and B, that's just going to be the calculation of the probability of A multiplied by the probability of B. Oh, I'm sorry about that. That's if they're independent. So the probability of B given that A has occurred. That's the formula that will always work. So thinking about the probability of A, this is just the probability of pulling a red card. So we know that there are 26 red cards in the deck, and there are 56 total, so that first ratio is going to be 26 over 52. Easy so far. So now we have to calculate the probability of B given A. So remember, this is B given that A has occurred. So the probability of getting another red card, that's what B stands for, given that we've already pulled and did not replace that red card. So again, we think of the same ratio, the number of good outcomes over the total outcomes. In this case, our total outcomes was at 52, but now that A has occurred, we pulled a card and we kept that card. Our total number of cards in our sample space has gone down from 52 down to 51. And then the number of good events has also changed because we originally we pulled out that red card. That's what A is telling me. And if I'm assuming that A has happened, which is what I'm doing here, then my number of good options has also decreased. So now there's no longer 26 red cards, there's 25. So that is my two ratios that I've got set up. I just typed those into the calculator. Again, if you're going to type them into the calculator, make sure you do parentheses. I'll verbally go through this. I'm going to type in 26 divided by 52, close parentheses, times, open parentheses, 25 divided by 51, and I end up getting, in this case, 0.2450. I'll write that up here, 0.2450. Again, the three significant figures that I need, 0.245 I would accept, 24.5% I would accept. Now this is the only type of problem where I'm really going to care about decimal places, and I'll point out on the exam when this occurs. But let's say you made a mistake. So what I'm writing up here in green is a mistake. And you calculate 26 divided by 52 for the first ratio, and you're multiplying that by 25 divided by 52 for the second ratio. In this mistake, it looks like the student forgot to decrease the total number of options by 1 because you're keeping that card. That 52 has to be decreased. If you calculate this out, you end up getting 0.2403. You'll notice that the three significant different digits is slightly off. 0.240 is slightly off 0.245. And on most typical problems, I'm not going to be that worrisome about that small difference. However, because this problem is making sure you can understand conditional probability, or the probability of something occurring given that something else has occurred, this is where I'm going to be picky about those decimal places. Don't get too hung up on that. I'll make sure it's very clear whenever that occurs. All right, so hopefully you feel good about this type of problem now. What we've done is we have covered all types of probability in that chapter 4 that we're going to be covering right now. I'm glad that you stuck with it for this video clip. Hopefully it helps. Let me know. Drop me an email and think if this helps. I'll continue to do this if it makes sense throughout the semester, but if no one's using these, then it does take me some time. So just let me know. All right, have a great weekend.